Hey, welcome to the Birnbaum Science Vodcast of the day. Today I'll be doing two things for you. First, I'll be solving this Rubik's Cube, and then I'll be showing you the spontaneous assembly of straws in a water solution. Well, I'm done with that portion of the vodcast, so now let's bring in the camera and take a look at what these straws have done. So I'll be explaining this later on in the vodcast, but if you just take a quick look, these straws have spontaneously assembled into an ordered structure. They're all kind of lined up. There you got these ones lined up here, and then these two kind of lined up on this corner of the water cup, bowl, whatever you want to call it. So the reason that these straws spontaneously assemble has to do with the Gibbs free energy equation. And so what I have it right here. So what the Gibbs free energy equation is that delta G is equal to delta H minus T delta S. And so what all these terms are is delta G, which is the indicator of whether or not a reaction is spontaneous. If it's negative, the reaction will proceed spontaneously. Is equal to delta H, which is the enthalpy of the reaction, basically determining whether the reaction is exothermic or endothermic. And then it's subtracted to that is the term which is the temperature in Kelvin. So this term's always positive because there's no such thing as negative kelvins. And then multiplied by delta S, which is the change in entropy. So when we examine this equation further, we'll realize that why these straws are able to assemble spontaneously. So when we take a further look at this equation, remember we're trying to get a delta G that's negative because this happens spontaneously. We're going to look at the two terms. These two terms are basically the two driving forces of reactions. We've got enthalpy and entropy. And so we know, because the definition of entropy is the amount of chaos in a system, that the delta S is going to be negative. It's decreasing in chaos. It goes from the straws are all mixed up to the straws are all contained in a little tight packed formation. So based off the definition of entropy, this term is going to be negative. The T, as I said, is going to be positive because Kelvin is always positive. So this term as a whole is going to be negative. So you're going to be subtracting a negative, which, as you know, with simple arithmetic, is going to be adding to the value of delta G. So as I said, this term is going to add to the whole value of the equation. So for delta G to stay negative and be spontaneous, this delta H term, the change in enthalpy, is going to have to be negative. And so what a negative change in enthalpy means is it's an exothermic reaction. It releases energy into the environment. And so that occurs when a system goes from a high energy state to a low energy state. And so now looking at these straws, you might be wondering, what are these energy states you're talking about? So as I said, the change in enthalpy is going to be negative, so it's going to go from a high energy state to a low energy state. So I drew a diagram of kind of the states that I'm talking about. So if you look, this is how the water kind of orients itself around the straws. And this is due to a property of water known as surface tension, which is basically water molecules stick together. They stick together very well. So it creates a kind of, the surface has this kind of film, this kind of strength to it. And the straw, when the straw interacts, the straw is hydrophobic, which means it doesn't like water. Water is repelled from it almost. So when you place the straw in, the straw, as you know, has round. It's a tube, so it's got ends and then this kind of round. If you look, this round surface. So the sides actually behave a little differently from the ends. So the sides, as I said, is hydrophobic. So the water kind of bends away from the straw when you put it in. So as you see, the water kind of bends down away from it. And so these curves, they're a form of energy. The water has to have a certain level of energy to maintain these curves. And so when you look, when I transfer it, and when they're touching, there's less curves because there's no longer any curvature. The word is meniscus. There's no longer any curvature of the water in between them. So if you look, it went from four curvy little menisci to only 2 menisci. So that is why when there is a negative change in enthalpy, it goes from a high energy state to a low energy state. when these straws come together by the sides. So the same property is true for the ends. So if you look at a straw, as I said, the side, which is the kind of the surface, the real plastic of this plastic straw, is what there is also attractive forces because there's a change in enthalpy given off by the ends. So if you look at this picture, this is a sideways view, a sideways diagram of a straw. It would be like so. The ends actually attract the water because it's kind of a lack thereof of the repelling surface, because obviously there's a hole in the straw, there's a lack of that plastic. So there's a meniscus curve in the opposite direction, and so when they join, you have, once again, you go from 4 meniscus curves here to 2 meniscus curves. So that's why when it goes from a high energy state to a low energy state, when the sides and the ends kind of line up and they form these parallel rows that you can see. Obviously I'm forcing it a little bit right now, but they form these parallel rows. So I've demonstrated to you the principles behind why this is spontaneous. So now let's take a look. Obviously the times before I had prepared them previously, but let's take a look and see them do it in action. So I'm going to mix them all up, and we're just going to watch them for a little while kind of form. Let's take a look, observe them in their natural habitat. Here they come. They kind of got this whirlpool going on. They're all going around. This is a high entropy state right now. But as you can see, some of them are kind of forming already. Ooh, look at these two are about to, see, those two just came together. So these are all, this is an interesting formation we got here. So right here you got the 4 ones in a line with next to 2 in a line. So as you see, the ends are attracted to each other, as well as the sides are attracted to other sides. So this is kind of coming up well. We got 7 of them kind of conglomerating over here. This guy is he'll work his way over. But as you can see, I just randomly mixed them up, and they're pretty much all coming together. If we waited longer, we'd be able to see them all form. But this is a pretty good demonstration. Here. We got some more. Ooh, yeah, that was nice, right? Okay, so now here's an interesting nuance in this whole demonstration. Is that so we have a negative term as I demonstrated here, and a positive term here. And so obviously delta G is negative when this temperature term is low. But temperature, as you know, is a measure of kinetic energy. So I can prove that if you increase this temperature, that I can make the delta G go up, and it will no longer be a spontaneous process. So as I said, temperature, measure of kinetic energy, can be demonstrated with the use of this toothpick. If I agitate the solution, which is basically the equivalent of adding temperature to it, we can make this conglomeration, the coming together, the attraction between the straws. We can see that it is no longer spontaneous. So if I keep mixing it, keep applying temperature, they will never form. So it is no longer spontaneous when you increase the temperature, or kinetic energy, which was clearly demonstrated by my use of the Gibbs free energy equation. Another way to make these no longer spontaneous is to get rid of the whole surface area idea. And so one way to get rid of surface area is you add soap. So if you look, I'm going to get them kind of together. So what soap does is soap destroys surface tension. I don't really know the exact chemistry of that yet, but I'm sure I'll learn it eventually. But I know that soap gets rid of surface tension. So if I add some soap in here, let's get some soap in there. Mix this up. They're no longer. They are gonna just be chaotic. There's no more. Okay. So that's just a nice little thing to show. So this has been a great vodcast. I think we've really